What's up, guys? Welcome back to Chem 1 BSI. My name is Roane. Today we'll be talking about some gas movement and combined gas laws. The first thing I want to talk about today is diffusion and effusion. So in chemistry, the definition for diffusion is a little bit different than it is in something like biology. But in chemistry, the diffusion is just the action of two gases moving towards each other and eventually mixing. I think in biology, the definition has to do with a little bit to do with concentration, but not for chemistry right now. This one is just two gases moving towards each other. Effusion is not the reverse of diffusion or anything like that. It's not the inverse. It is just the passing of gas molecules through a small hole in its container, and it's usually from an area of high pressure to low pressure. So effusion would be if you had some sort of container. Sorry for the bad drawing. If you had some sort of container, and in this container you have a bunch of gas molecules, okay, and those are all moving around. If you get a hole in this container, which is what I've drawn right here, if you have a hole in the container, the rate that those gas particles shoot out of that hole is the rate of effusion, and just those gas particles coming out of the hole is effusion. So like I said, effusion is just the gas molecules coming out of that hole. The rate of effusion would just be how fast those gas molecules are coming out of the hole. Speaking of the rate of effusion, Graham's law states that the rate of effusion is proportional to 1 over the square root of m. It is important to note that m is not molarity or anything here. M is molecular mass. Okay, so make sure you don't get that mixed up with anything. If you see a rate of diffusion question, you make sure you know what that m stands for and know how to calculate it. Also, side note, you probably won't need to use this that much, but you can also use this same formula for the rate of diffusion. It's the same thing, but that's not really important. However, what is important is the relationship between the rate of effusion and molecular mass. So some of you might be thinking about how molecular mass and effusion relate to each other. These two are inversely proportional, and what I mean by that is if the rate of effusion, or if the molecular mass goes up, the rate of effusion will go down, and if the molecular mass goes down, the rate of effusion will go up. And what that means is, like illustrated in this graph, sorry that the writing's kind of going over it, but illustrating this graph is that the lighter gases like hydrogen and helium, those will have the highest rates of diffusion or effusion. And then as you get heavier, when you get to things like carbon dioxide further down here, or oxygen gas, those are much heavier. So the heavier your gas molecule, the lower your rate of effusion / diffusion. So we're going to be talking about some gas laws now. There's 4 gas laws. This chart only has 3. Boyle's law, Charles' law, and the Gay-Lussac's law. Also, some people call it Amontons. So if your professor calls it Amontons, make sure you know that. But they all, or some of them, have different relations. So Boyle's law, pressure and volume are inversely proportional, and by that what I mean is if your volume is increasing, then that means your pressure is going to decrease. It's the vice versa with Charles' law and Amonton's law. As volume increases, temperature will also increase, and as pressure increases, temperature will also increase. That might be important. I'm just going to write it down. This is inverse, this is directly, this is directly. And this is just standing for inversely proportional, directly proportional, and directly proportional. There's also the fourth law is Avogadro's law, and this one relates volume and the amount of moles. Again, this one is directly, so if one of them increases, the other one is going to increase as well. However, if you combine the three in the chart here, Boyle's, Charles, and Monton's, you will get the combined gas law. And that relates all three of those variables, excluding moles here. So moles isn't included in this combined gas law. But pressure, temperature, and volume, the combined gas law takes all of them and relates them all. So if you have a pressure, volume, and a temperature at one point, and then you increase one or two of those, you can find the third missing variable. That's the combined gas law. And then the formula that you will all have to become super familiar with is the ideal gas law, but we're about to get to that. And another important thing, volume you want to be dealing with in liters, okay? Always in liters. So if you get milliliters, you usually want to change that. Temperature is in Kelvin, so not Celsius. And you guys know if you have Celsius, to get to Kelvin, you just add 273. Pressure can be kilopascals or atmospheric. It can also be Hg and a couple of other things. But kilopascals or normal pascals and atmospheric are the two you use the most. Number of moles is pretty straightforward, and the ideal gas constant. So the ideal gas constant changes depending on what values you have, and we'll get right into that as well. So the ideal gas law. This is the ideal gas law. We have pressure, volume, moles, temperature, and the ideal gas constant. So the ideal gas constant, I believe, has to do with whatever type of pressure you have. Okay, so like those two pressures I was talking about, these are the ones we'll go over. So if you have kilopascals or atmospheric, you will be using two different types of ideal gas constants. Okay, so just make sure you guys don't don't use the wrong ideal gas constant because it'll lead to a wrong answer. So the ideal gas constant for ATM or atmospheric, is going to be 0.0826, and the decimal points can change a little bit depending on your professor. And the kilopascals one is 8.314. Okay, so depending on what type of pressure you have, you will have to use a different ideal gas constants. Just make sure you guys know those. And all of the other ones on top are just basic things. Again, we'll just put K, moles, liters, and ATM/kilopascal. So those are all your variables. Usually you're just given them. Sometimes you have to find them. But we'll get into a practice problem right now. So our practice problem is how many moles of a gas will a 1,250 milliliter flask hold at 35 degrees Celsius and a pressure of 1.2 atmospheric. So if you have a problem, the first way you want to look and decide if you're using the ideal gas law is if you have all four different variables. So if you have moles, if you have pressure, volume, and temp. If you have a question that gives you some of these bits of information and asks you for some of these bits of information, you're probably going to be using this gas law. Another way is if it's telling you that you have like a pressure at one point and then you expand or you contract and you change your pressure or you increase your pressure, if you're going from one pressure to another, you might not be using this law. This law is just for at one point, what is to find your missing variable. So PV equals nRT. Remember, we have pressure, it's an atmospheric, so 1.2. We have volume, but we have to convert that to 1.25 because we need liters. We're looking for moles, so we don't have N. Our R, because we have atmospheric, it's going to be 0.0826. 0.0826. And our temperature is 35 degrees Celsius, but we have to change that to Kelvin, so we have to add 273, and that is going to equal 308 Kelvin. 308 Kelvin. Oh, sorry. Now all we have to do is do the math. So 1.2 times 1.25, you get 1.5, and then 0.0826 times 308 equals around 25.44, and then you just divide both sides by 25.44, and you'll get 0.069. That's what we'll say. So we get 0.069 moles of our gas, and that's how you use the ideal gas law. So thank you guys. I hope this video will help you guys with some of your gas laws. If you have any questions on the worksheet or on this video, or you want some more practice, feel free to do the worksheet we have in conjunction to this. But I hope this was helpful, and I hope to see you guys in office hours. Thanks, guys.